Okay, thank you, Dave. A recurring theme, as we saw in Jung's talk in waveform inversion, is the separation of scales. For example, in migration, which in most forms is just a linearized waveform inversion, we separate the model into a long scale background model and a short scale reflectivity model, and then we try to invert for the reflectivity. The work that I'll show here today is based on a similar idea, which is to separate amplitudes and travel times in the data. And travel times, of course, correspond to the long scale background model, and amplitudes correspond to the reflectivity. So in a sense, you can view this separation as a separation of scale, but for the data. So I'd like to start with a simple example just to motivate why this separation might be useful. So for this example, I have a source function f, and my model consists of only two parameters, alpha and tau. The simulated data d sub s described by the forward modeling equation are simply scaled, shifted versions of the source function. So clearly for this example, alpha corresponds to the amplitudes and tau corresponds to the travel times. Suppose now that we want to find the model that minimizes the difference between simulated data and observed data d sub o, which I've plotted in red. So for this example, because I only have two model parameters, I can actually go ahead and plot the entire objective function, which you see in the top panel. First notice the white star, which is the location of the global minimum. And notice that because we are using the same modeling for both the simulated and observed data, the error at the global minimum is 0. Notice also the valleys, if you will, in the objective function, and these of course correspond to the local minima. And then the pink dot indicates the initial model, and if we compute data using this initial model, we get the black curve shown in the bottom figure. So what you should notice here is that first of all, the black curve and the red curve, so the simulated and the observed data, differ by more than half a cycle. And also that the pink dot and the white star do not lie in the same valley. So what this means is that we expect to see cycle skipping if we don't use some global optimization method. So if we were to use a local descent method, the model that we would recover is indicated by the pink arrow. And then if we compute data using this model, we would get the black curve shown in the bottom panel. So now the black and red curves differ by exactly one cycle. So actually this model does match the data better than the initial model, but obviously this model does not correspond to the global minimum. So suppose now that we have a different way to estimate the travel time shifts. We have a better way to estimate the travel time shifts. For this example, obviously I could use cross-correlation if I wanted to estimate the travel time shifts. And so with these shifts, if I were to first shift the observed data before computing the objective function, this is the new objective function that I would obtain. And what you'll see now, obviously, is that the pink dot, so the initial model, now lies in the same valley as the global minimum indicated by the white star. So if we were to do some local optimization with this objective function, we would easily converge to the global minimum. And as I mentioned before, for the global minimum, the simulated and the observed data are exactly equal. So what this example demonstrates is that by separating the travel times and amplitudes and by using a different method to estimate the travel times, we're able to better estimate the amplitudes. For this example, I knew the correct travel times, obviously, but in practice we'll use dynamic warping, which you just saw an example of in Jung's talk. So in effect, what we're doing here is we're handling the nonlinearity in the inversion caused by the travel time shifts using a different method, which is dynamic warping. And the nice thing about dynamic warping is that it is guaranteed, at least in the 1D case, to find the shifts that minimize the difference between the simulated and the shifted observed data. So let's move on to a more complicated example. In conventional waveform inversion, our goal is to find the model that minimizes this objective function, which is the scaled norm of the difference between simulated data p and observed data p tilde. Because of the large number of unknowns that we need to invert for, in waveform inversion, of course, it's not practical to completely map the objective function like I did for the simple example. So what this means is we're limited to local descent methods. So for example, steepest descent, conjugate gradients, and variance of Newton's method. So for these methods, we need to compute the gradient according to this equation. And here, delta P is the residual. L is a forward modeling operator, and L star is the adjoint. And in conventional waveform inversion, the residual is simply the difference between simulated and observed data. Once we have the gradient, we can update the model by adding to it the gradient scaled by a step length. This equation here is for steepest descent, but there are better alternatives, and actually for the examples I'll show, I use a nonlinear conjugate gradient method. But in any case, we always need to compute the gradient. So to briefly summarize, to minimize J, we iteratively update the model by first computing the gradient and then scaling it by a step length before adding it to the model at the current iteration. The most important step in this process, obviously, is the computation of the gradient, simply because it directly influences the direction that we move along the objective function. So in this presentation, I'll show examples of waveform inversion making a single change, and that change will be the residual that I use in computing the gradient. So the different residuals that I use are listed in this table here. The first is the data residual, which again is the difference between simulated data P and observed data P tilde. And waveform inversion using the data residual is just the conventional waveform inversion that many of you are familiar with. Second is what I'll call the amplitude residual, and the difference between the data residual and the amplitude residual is that for the amplitude residual, we need to shift the observed data P tilde before subtracting from the simulated data. Finally is the amplitude and travel time residual, and you can see that this residual contains the amplitude residual, but it also contains an additional term which is actually a travel time residual. So as I mentioned before, we need to estimate the travel time shifts tau between simulated and observed data, and to do this we use dynamic warping. So the first example I'll show is of least squares migration, or LSM. And in linear least squares migration, we need to we model data using so-called Born modeling. And for Born modeling, we need to solve two wave equations. The first equation describes the incident wave field P naught, which is modeled in a smooth background slowness model S naught for a source function F. The scattered wave field, or the reflected wave field P, is also modeled in the smooth background S naught, but for a different source function. And the source function is the negative second time derivative of the incident wave field scaled by the reflectivity R. And R, the reflectivity R, as I've defined here, is the difference between the slowness squared and the smooth slowness squared. So what's important here is first that in migration, the background model never changes. So the background slowness S naught never changes. And also the reflectivity, although strictly speaking here it has the same units as slowness squared, the reflectivity does not directly affect the travel times. And the goal in migration here is to invert for the reflectivity given the background slowness S naught, which we assume correctly models the travel times. And this is a big assumption actually, because we need to, of course, estimate the background slowness using the same data that we'll eventually use for migration. So a relevant question is, what happens if we have errors in the background slowness? So to test this, I'll use the Marmousi model, and this is what I'll call the true background slowness. And what I mean by true here is that this is the background slowness that I use in combination with the true reflectivity, which I'll show you next, to model observed data. So this is the true background slowness, and this is the true reflectivity. And again, this is computed as the difference between the slowness squared, which I've not shown you, and the smooth slowness squared, which you just saw. And our goal, again, is to invert for this reflectivity. So the first iteration of LSM, of least squares migration, is essentially reverse time migration. This is not a particularly good RTM image, partly because I'm not using any preconditioning in my implementation of least squares migration. So for example, in this case, we could easily correct for the illumination, the uneven illumination, with a diagonal approximation of the Hessian. But actually, with more iterations of least squares migration, we expect to account for the Hessian. So with more iterations, we expect to see illumination compensation as well as compensation for off-diagonal terms in the Hessian. And this is the LSM image after 20 iterations. So compared to the first iteration, you can see, obviously, the more even illumination and also better focus reflectors. And this, of course, is the motivation for least squares migration, this much better image. But, of course, this image comes at a much higher cost compared to RTM. So comparing to the true reflectivity, they match pretty well. And this is a data domain inversion, so we need to look at data. These are the observed data computed for a shot located in the center of the model. And these data are modeled using the true background slowness and the true reflectivity. Comparing now to the simulated data modeled using the true background slowness and now the reflectivity computed using 20 iterations of least squares migration, we see they are almost identical. The data residual behaves as expected. So here I'm showing the normalized norm of the data residual as a function of iteration number. And what we see is that the residual decreases monotonically with increasing iteration number, and that it looks like after 20 iterations the inversion has converged. So the question we asked before is what happens if we have an error in the background slowness model. So to test this, I scale the true background slowness by 95%. So I introduce a 5% error in the background slowness. And then I do least squares migration using this incorrect background slowness model. And this is the image that I obtain. So again, this is 20 iterations of least squares migration. And comparing this to the least squares migration for the true slowness, we see that reflectors are misplaced and are also defocused. And this, of course, results from errors in travel time in the simulated data due to the error in the background slowness model. So to address this problem, we can use a different residual in computing the gradient. So the previous examples used the data residual. And the issue with the data residual is that it contains both amplitude and travel time errors. So what I mean by that is if you were to shift the data by some travel time shift, or if you were to scale the data by some amplitude scale, in either case you would change the value of the data residual. In contrast, the amplitude residual, if we assume that we're able to correctly estimate the travel time shifts tau, the amplitude residual only measures amplitude errors. So it might make sense to use this amplitude residual in migration because intuitively it makes sense to use amplitude errors to invert for the part of the model that only affects the amplitudes. So I'll use a capital A to indicate when I'm using this amplitude residual in the inversion. So LSMA indicates least squares migration using the amplitude residual. And this is the LSMA image still using that incorrect background slowness model. So comparing this image to the conventional LSM image, we see a pretty dramatic improvement. The reflectors are more focused and are more continuous, despite the fact that this image was still computed in using completely the wrong velocity model or slowness model. Comparing now the LSMA image to the true reflectivity, you'll see that reflectors are still mispositioned. And this should not be surprising because, after all, we're still doing migration with the incorrect background slowness. So we can't really expect to image reflectors at the correct location when the kinematics of the wave field are still incorrect. Again, these are the observed data computed using the true background slowness and the true reflectivity. And these are the simulated data computed using the incorrect background slowness and the reflectivity computed using LSMA. So what you'll notice is that the simulated data and the observed data more or less look like shifted versions of each other. So in other words, what we can say is that their amplitudes match, but their travel times do not. So this is analogous to the simple example I showed at the beginning, because what we've done here is that we've used, by using an alternate method, which is dynamic warping, to first estimate the travel times, we are better able to match the amplitudes. Let's look at the data residuals, the residuals for the different inversions. So this is the same curve that you saw earlier. This is the data residual for least squares migration for the true slowness model, the true background slowness. This blue curve is the data residual for LSM for the incorrect background slowness, and what you'll notice is that in the first 2 iterations or so, the residual decreases, then it actually increases. The reason for this increase is only because of the way I've implemented the line search. So what the line search does is that if it cannot find a step that decreases the residual, it'll actually take a step anyways and increase the residual with the hope that it might eventually step out of a local minimum. But that doesn't seem to happen here. The red curve shows the amplitude residual for LSMA for the incorrect background slowness. So remember, the amplitude residual, we first need to shift the observed data before subtracting from the simulated data. And then finally, this is the data residual for LSMA for the incorrect background slowness. And what's important here is that this last curve, this data residual, is not used in LSMA. So in other words, in the code for LSMA, nowhere do we actually compute this data residual, which is why you kind of see this perhaps strange behavior compared to the other curves. But what's important here is actually that this data residual illustrates that so because LSMA increases the data residual, because this hollow red curve increases, what that's telling us is that there is no way that you can compute this image using conventional least squares migration, because the goal in conventional least squares migration is to minimize the data residual. So with the remaining time, I'd like to briefly show you some examples of using a similar approach in full waveform inversion. So this is the true slowness model, and our goal in FWI is to invert for this model. And this is the initial model that I'll use, and this is just a highly smooth version of the true model. And this is the result of FWI after 20 iterations. So you can see that this is still far from the true model. So let's see what happens now if we use a different residual. In this case, we're going to use the last amplitude and travel time residual highlighted in red. And remember, this residual contains the amplitude residual, and it also contains an additional term, which is a travel time residual. And the reason we choose this residual is because in FWI, we're inverting for slowness or velocity instead of reflectivity. So we expect to see both amplitude and travel time errors, so we use this amplitude and travel time residual. And this is the result after 20 iterations of FWI using this new residual. And compared to the conventional FWI, this model better matches the true model. So to summarize, I think it's known that convergence to local minima results partly from large travel time shifts. And so what we've done here is that we've handled these travel time shifts using a different method, using a more robust method, which is dynamic warping. And it seems that by separating these travel times, we're able to improve our migration and inversion results. Thank you.